useful for you guys, and it makes a better session too, right? Okay, so things should start being recorded. Ooh, I have a little transcript. Okay, how do I get rid of the thing? There we go. Okay, perfect. Okay, so the first thing on the list was convolution, Laplace, and inverse Laplace transform stuff. So if you're wanting to do something with convolution, then you really have kind of two options now. So when we first introduced convolution, we had it as the definition of that integral transform. And let's see which side works. Yeah, so do we see that line clearly with the different resolutions floating around? If you don't see the line, let me know, and I can use the thicker one. Or if we have a preference, you can let me know as well. Are we all good? Okay. All thumbs up, so we're going to say good. Okay, so I'll use thicker line. Okay, so if I give you two functions, say f of t, and my convolute that with my g of t. Okay, so here you really have two options. You could use the definition. So the definition we integrate from 0 to t. And here, because we know that the convolution of f with g is the same thing as the convolution of g with f, since we know this is true, it doesn't matter which one of these two things you shift. You just have to make sure you shift one of the two, right? So from here, we're going to integrate with respect to a new variable tau, right? And one of these terms will just be f of tau. In the other term, what we do is we flip and negate the thing. So we take g of t minus tau. Okay, so in terms of the thing that I did previously with vectors, you kind of treat f as a vector like this, and you treat your g as a vector like this. When I was doing the thing with the hospital analogy, I took the f and I fixed it going this way, and I took the g, if this is, say, my starting point, I took the g and I wrote it like this, where I flipped it going this way. And then I just took this thing and I shifted and computed that weird sum product thing. That's why you're doing this term here. Okay, so if you're doing something with convolution by definition, then you use the definition, that guy, right? So in practice, one thing that came up as an error, and I'd call this a Calc 1 error, would be when I gave you a function where one of these things was piecewise defined and you try to integrate everything out. If you do that, basically when you take your f and multiply it by your g, so if this thing is piecewise, then this thing will obviously be piecewise. So you'll at the end of the day, you'll have something like this of some branches. So it might be, say, I'll just call it capital F1 if tau is less than or equal to 0, less than, say, t1. And it'll be F2 if I'm between t1 and t2, so on up until Fn, where I'm greater than or equal to, what would that be, Tn, right? Yeah, 2, perfect. Okay, so when you go to integrate something like this, just I consider this a Calc 1 type thing, but you have to consider the different branches, right? So you have to ask, what if my time, t, is between this range? What if my time t is between this range, etc.? So just graphically, that should make a lot of sense. So if I plot some function, say if I have a function that does this, and then that, and then that, and then that, and then that. So if I asked you to integrate this thing, right, you'd have to integrate it here first, and then the function changes, so you have a different integrand. So then you have to integrate it again, so green, up to here. And then you would have to integrate it again up to here. And then you'd have to integrate it again up to here. And then you'd have this last one over here, right? So because of that, you really are considering these different groups between, oops, there we go, between these different values here, right? So you have to consider what if t is in each one of these little regions. Which I shouldn't draw that, but like, what if it's in each one of these little bits here? Okay, so if I ask you to do something with convolution by definition, kind of less likely because we have a better theorem to evaluate these. But if I did, then you would need to consider each one of these regions for different values of t and chase that out. So I forgot what homework assignment that was, but just to rehash that with a particular example that's before or after convolution. Yeah, so that's testing those with convolution. So it would be before that, probably. Yeah, so for this problem here, if you want to chase this out by definition, here you do your shifting thing for your choice between this or the exponential. It doesn't really matter there. It's probably a little bit easier to put it on maybe the sign. It's personal preference. It doesn't really matter. And if I pull up the solution for this, here you have to consider all of those things. So here, if I take these two things and convolve them together, I get this. And then now I have to consider the different branches for this piecewise defined function here. Since I put the tau inside the f function, I can control what capital T is pretty easily. I don't have any of the kind of weird workaround stuff to do. So because I did it here, I can see a thing. So convolution, I don't believe is on the sheet. Let me pull up the final sheet. So basically, final guidelines, detailed guidelines, perfect. Okay, wrong one. This final guidelines. This is so annoying. I want to remove this for the last time. Okay, gone. Okay, there we go. Okay, so these are the things that you get. So you do get the definition of convolution. So you don't have to memorize that one. You do get that one. So literally on this final guidelines that is uploaded to Learn, this last page, this is the final sheet that you get. So quite literally, this exact page is on the final. So you get all of these things. And it's, I believe I made it such that it's detachable. Okay, I'll stop sharing screen. Actually, that's not fair. I think it's detachable with the extra side of workroom on the other side. So yeah, so this is a complete list. Do note this isn't actually cut off. That's just because of the template that I'm using and the way that the spacing worked. I could manually split it. Nevertheless, this is the sheet. So you do have convolution and convolution theorem. Okay. So what was I? Yeah. So here you have to consider each value of t to evaluate this out, right? So here you just do what if t is less than pi? Oh, in that case, I'm just always 0. Oh, what if t is between pi and 2 pi? Well, I get 0 up to here. So then I change it from the integral from pi up to t and chase that out. And then finally, the last one, what you really just do there is you plug in, instead of t, you plug in your 2 pi. And that's the final solution there. Okay, so keep that in mind. If you have a piecewise defined thing, you have to do that. Okay, so this is one way that you could attack it, but there is a better way, right? So instead of doing this, if I remove all of this, what you could instead do is use the convolution theorem. Okay, so what is the convolution theorem? So what it quite simply states is that the Laplace transform of the convolution, so the Laplace transform of this type of a product, because this is a product of two functions, is the Laplace transform of the product, or the product of the Laplace transforms. So this guy here, times Laplace of g of t. Okay, so how does this help me solve this? Well, if I had to do everything by hand and compute Laplace transform by definition, it wouldn't. But I have this handy dandy Laplace table here, right? So since I have a nice Laplace table, I can freely compute Laplace transforms and inverse Laplace transforms of a lot of different functions, right? So what you could say is, hey, if I take Laplace inverse of both sides, that would give me that this is equal to the inverse Laplace transform of the product of these Laplace transforms. And at any point in time, if people have questions or comments or want extra details, feel free to interrupt like a regular class, right? It's just because we're online and I can't see your smiling masks, doesn't mean you still can't interrupt and all those good things. So you could, there's like a raise hand feature, or you could type in chat, any of those type of things. Okay, so the convolution theorem tells us that this is just going to be the inverse Laplace transform of these. Okay, so what if, for instance, I knew, and I won't necessarily run this to completion, but let's see if I knew that this thing was t to the 6th, and this other g here was e to the x, sorry, e to the t. Okay, what are the motions that I would do here? Well, what I would do is for the t to the 6th, I would go over here to my handy dandy table and say, hey, t to the n into 6. So I plug 6 here. So it's 6 factorial over s to the 7. So here you could say, oh, this is just 6 factorial over s to the 7. So how many questions? I'm comfortable saying that now. Let me actually pull up the final. I'm going to stop sharing screen because I'm actually pulling up the final. Let's grab the print version. So there's 11 questions total. One of, like, some of them have subparts to like hand you through a problem instead of just giving you a raw big problem and say go have fun. The first one is the standard true false type things. So little few parts there, and then there's some compute Fourier series, yeah, some stuff with basic computations there. There's some stuff with, I'll stop looking at the actual thing, but there's some stuff with obviously solving the PDEs on there. There's some stuff with the basics of convergence. So like, here's a sequence of functions. Does it converge? If so, like, show it converges. You don't have to do delta epsilon, anything like that. Just evaluate the limits type stuff. So yeah, so there's a little bit of everything that we've covered in the last half. And there also are some solving ODE stuff, but you can feel free to use Laplace. Like, Laplace works on any ODE that we've solved that's linear, as long as it's linear. Laplace will work on them. So there's nothing nonlinear. I'm free just telling you that now. That was the first half, right? Exact and separable. Those are the only types of nonlinearity things we've worked with. So I'm free just telling you there's nothing nonlinear, even though it's on the little guide sheet. The previous guide is just everything there, right? But there's nothing nonlinear, so you could use the method of Laplace to solve everything, right? Yeah, so handful of ODEs, all that good stuff. Do keep in mind you have 2.5 hours. So it's kind of scaled up linearly with the amount of work. Yeah, so 11 might sound scary, but 2.5 hours. Okay, so now for this term here, well, oh, I might have forgotten what e to the t is. So you look in the list, you find, oh, here's e to the at. So here I just have e to the 1t, so that's just going to be 1 over s minus 1. So then you write this as 1 over s minus 1. Okay, now how do I compute an inverse Laplace transform? Uh-oh, I'm stuck. Well, you're not actually stuck, right? So here I have this table again. So if I can rewrite the thing that's inside here, if I can rewrite this term here as a bunch of sums of these things here, I can use the linearity of the inverse Laplace transform to break it down. So in this case, this is something that would be too computationally difficult for me to give you for a final question. Just, yeah. But what you would need to do at this point is, hey, you could take the 6 factorial and put it out front if you wanted. So I'll just do that. You could do this and erase it here. Sometimes that can be useful. Sometimes it can be useful to keep the coefficient. It just depends on the numbers, but mathematically it doesn't matter. Then from here, I have this product of things. So I need to rewrite 1 over s to the 7th, s minus 1, as things that are in my list. So if you look at the list, you could look for as long as you want, but that term that I just wrote is not here. So what you need to do is split it in terms that are here. So if I have something like this, the natural way that you could try to split it up is by using partial fractions. And it turns out that if you do that, well, a bunch of the terms will be like 1 over s to some power, or a constant over s to some power. Hey, each one of those is a t to the n. Each one of those is one of these, right? So you might not have the right constant, so you multiply, divide by it to fix that. Then the last term I'd have is going to be a 1 over s plus or s minus 1. So that'll be something like this, potentially. It could end up being something like these terms, depending on how things chase out in some contexts. But what you do is you make your partial fraction ansatz. And again, this is way harder. It's not hard, right? It's just computationally very annoying because Heaviside method basically stops immediately. Over s to the 5th plus d over s to the 4th plus e over s to the 3rd plus f over s squared. When I came up with this one, g over s plus f, I was not thinking about how it would expand out here. But yeah, it's kind of the obvious way to expand. So for Heaviside method, which coefficients can we get? There's two coefficients here that we can get via Heaviside method. Which two? Any ideas? Okay, so I'll just tell you. It will be, where's this? It will be this term here and this term here. So let's, yeah, A and F. Let's just do the Heaviside method. So we'll set this up. We won't solve it all the way because there's going to be a system of B, C, D, E, F, G, 6 equations with 6 unknowns. So obviously, I'm not going to give you something that bad. But here, what you could do is you could say, hey, if s is such that this term is 0, so if s is equal to 0, I'd take this whole thing and I would multiply it by s to the 7th, right? So if I multiply by s to the 7th and plugged in 0, this term goes away, this term, this term, this term, this term, and this term, all of these terms go away. Like, they're gone. Similarly, oops, they're really gone. Okay. Similarly, this term here would go away. So, and this term here would go away. So in this case, I'd have 1 over, so plug in 0. So I'd have 1 over negative 1 is equal to a. Okay, so a is just equal to minus 1. Done. That's it, really fast, right? Now, if s is equal to 1, this term goes to 0. So multiply by s plus 1, at least in your head. And here you'd have 1 over 1 to the 7th. So 1 is equal to f. So f is equal to 1. Okay. Now, to solve for the rest of them, it's just going to be god-awful in this case. Like, there's no way around it. You have to solve a system. And here I'm kind of out of nice numbers for s, right? So the next one, I would say pick minus 1, and then just try to pick maybe like 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So pick your 6 constants, get 6 equations with 6 unknowns, chase that out. You will not have something this bad on the final, okay? You might have something like, maybe if I did this to the 3rd or 4th power, something like that could be reasonable to do. So yeah, just don't set up a matrix and try to invert the matrix. If you want to solve the system, do elimination. Yeah, so when I do, if I were to plug in s, sorry, I wasn't paying attention there, but if I were to plug in s is equal to 0 directly, things blow up, right? So what I'm doing, basically, Heaviside method is a way of avoiding multiplying everything out to get that big polynomial thing. So what you do with Heaviside method is you identify a term that you can plug into 0 to make one of these things, like the biggest power over here, blow up. Then what you do, so what I'm formally doing is in my head, I'm multiplying by s to the 7 on both sides, right? So when I do this, these cancel. So this cancels with this, and this cancels with this. Here I get a s. Here I get a s squared, s to the 3rd, s to the 4th, s to the 5th, s to the 6th. And here I get a s to the 7th. So in my mind, I'm saying, like, hey, I'm ignoring this term here, and I'm ignoring all of these terms that don't have a s to the 7th, or the highest power of s minus whatever my root was, and then I'm just plugging in 0 into the resulting expression. Okay, so that's what you're at least mentally doing with Heaviside. So, yeah. And the nicety is that it's not too difficult to do that in your head, right? Everything that's not divisible by, in this case, s to the 7th, those terms get ignored, and the rest of them I ignore the s to the 7th term, then you get your equation. So that's not bad to do, and it saves you a lot of work, right? So like formally here, if I didn't do Heaviside method, I would have what, 6, 7, 8. So I have an 8 by 8 matrix to solve, right? I changed that to a 6 by 6. So it's not the best here because it's still a hard problem, right? But like hard in the sense of computationally difficult, or that's an easy computation. You know what I mean? It's like you don't want to do that by hand. But it reduces it dramatically, right? So if you just think of matrix multiplication, actually here you'd have like matrix inversion. So matrix inversion, generally speaking, in the worst case scenario is O of n cubed for some, for bad cases. So here I kind of reduced my work from something like 8 cubed to something like 6 cubed. And if I'm doing multiplication instead, that'd be squared. So that's a dramatic reduction of work, no matter what operation you do. Okay, so can we use properties of even function definition? So Laplace transform, when you chase this guy out, this isn't even, right? It starts at 0 and it goes up to t, right? So even an oddness doesn't help you directly because it's not integrating over an even interval, right? So your bounds, so for Laplace, you're integrating from 0 up to t of your function, e to the minus sx dx. So evenness and oddness don't really help you here, right? They help with Fourier because we integrate from negative infinity to infinity, or if I'm doing the finite dimensional ones, tau over 2 to tau over 2, right? And these intervals I'm integrating over 0, so I can use even and oddness. Now, you can do different definitions. We don't do this at this point, but you can build different definitions of the Fourier transform. One of them, instead of going up to t, you chase this out to infinity, and you can include the t in here. So just like with when I'm doing Fourier transform, I have that t sitting there. So you can include a t, I believe, there to talk about that. You can also do the double-sided Laplace transform and do this. And if you're working with those, which you're not for this course, but if you're working with those, then you can use even and oddness. So yeah, but the issue there is this term isn't even or odd, right? It either exponentially decays or exponentially grows. So you would need the function itself to look like an exponential. So it's still kind of mostly useless there. But for Fourier, I'm dealing with basically this with an I in front of it. I call S by a different name, call it omega, but that's basically your Fourier transform. Here, now that I put that I have sines and cosines. Those are periodic, so you can use even and oddness. Yeah. So are there any other questions on doing things with convolution, Laplace, and inverse Laplace? So for inverse Laplace, oftentimes the reason why we do partial fractions is purely because in this list, I don't have the expression without doing partial fractions to simplify it, right? Like if you get a problem where you multiply two things together and it's directly in this list somewhere, then you don't have to do partial fractions, but it rarely ever will that be the case. Okay, so if I wanted to finish this, I would do this partial fraction decomposition, get these coefficients. So let's just clean this up a bit and make a few assumptions and show how to finish this problem. Okay, so if this was the case, you're being mean. Now you get to see how horrible my OneNote skills are. I'm better at Paint still, but I've gotten better at OneNote. Okay, so The thing I hate about OneNote is the whole exporting thing just breaks half the time, in my experience at least. Okay, so now let's suppose that I know what A through F are. Okay, so I did that partial fraction decomposition. I get this. Okay, so now how can I possibly chase out to do things? Well, the first thing I'll do is linearity, right? So I'd rewrite this as my 6 factorial. Here I have my Laplace inverse of my A over S to the 7th plus, I'm just going to put dot, dot, dot for all of these terms, plus I'd have this last term, so that'd be Laplace transform of G over S. And I used round brackets. I'm not going to. Plus here, I get this Laplace transform of, in this case, I'll just pull out the F, and I need an inverse there, of 1 over S minus 1. Okay, so this last term, and close brackets. Okay, so if I look at these different terms, since this is S to the 7th, in this case, if I go to my chart, I'd have n is going to be 7. Or sorry, n is going to be 6. So I need a 6 factorial above. Okay, so hey, here I actually have my 6 factorial. So I could pull this 6 factorial on the inside, and I could rewrite the first term. Well, that would be 6 factorial over S to the 7th. So that's just going to be my t to the 6th. Okay, so the next term would need a 5 factorial, right? Or sorry, 7 factorial would need a 6 factorial, 5 factorial. So here I would have a 6 left over, t to the 5th plus, and this pattern will continue down over to here. Well, this 1 over s is just t, right? Let me just double check that. 1 over s is just 1. So for this last one, I'll just end up with a plus 6 factorial there. Okay. And then over here, I'm going to have my f, oops, I dropped my coefficients, times a, times b, times g. And at the end, I'll have an f e to the x. So that's how you would chase this term out here. So I'm using this fact that I have this thing factorial sitting here, and I'm really just kind of plugging that in and pulling the a out, right? So pull out these coefficients, put the part of this that you need back in, and then you can chase these out. You can do it without doing that. It just makes things a little messier. You get the same answer in the end. Okay, so that's what I'll call doing convolution, Laplace transform, inverse Laplace transform. Questions on any of that? So in practice, yeah, if you want to solve PDEs, you can take the Laplace transform, solve for the thing, take the inverse Laplace transform. You might need to do partial fractions in the middle. Here, you can use convolution by taking Laplace transforms, multiplying them together, and then computing the inverse Laplace transform, doing whatever you need to chase that out. Are we all good on that topic? Then to do a particular example to full completion, I could, if someone wants, or I could switch over to solving the separable PDEs, which is worth about 14%. I did it earlier. The vast majority of it is going to be post-midterm, but you do need pre-midterm to be able to do some of the post-midterm stuff. Basically, I'll give you a, yeah, I'll freely tell you, I'm not going to give you a word problem with circuits. So yeah, that's not going to be a thing. So I'll freely tell you guys that. And I can do that since it's recorded and anyone can watch the recording. But yeah, so, and you can also tell your peers and all that good stuff. But yeah, so those will explicitly not be on there, at least directly, right? I could give you an equation that models that. Yeah, I'll do the Fourier series stuff. But yeah, so the focus will basically be on everything that we did after we introduced Laplace transform. Okay, so you need to know all the Laplace transform stuff there. Okay, so PDEs. What if I give you, so I could come up with a random one, or I can just grab from the homework assignment. Yeah, this one. So I will grab this one from the homework assignment and I will solve it. Okay. So I'm going to change the initial condition though, so I won't copy all of that. Okay. Oh yeah, tiny little text. There we go. Okay, and let's blow that up. Okay, so we're going to solve the heat equation with these boundary conditions. These are different than the boundary conditions I did previously in class. And so I have to think of a function that matches these boundary conditions. Well, I'll just tell you that u at x comma 0, I'm just going to say that that has appropriate series. So it has whatever you need, 0 to infinity of whatever function you need there. We're just going to freely assume that we have a function and we can compute its Fourier series. Okay, so on the, yeah, I won't make anything out there. So yeah, so we'll freely assume that. So on the final, I could give you something where I don't give you the Fourier series, and some points could be allocated towards finding the appropriate Fourier series, or I might just give you some Fourier series for the bounds. Okay, so those both are possibilities there. Okay, so here it turns out that this will be, I need to expand it out into weird bases. But yeah, so the issue with coming up with the random question here is I have to come up with a function that matches these boundary conditions if I want to legitimately get an actual solution. Mathematically, it's fine if you don't match the boundary conditions. It corrects itself in infinitesimally small time, but nevertheless. Okay, how do we attack this problem? Well, actually, I'll make it a little, now I'll leave the mu in. Okay, so how do I attack this? Well, this is really ut is equal to mu uxx, okay? So I'm going to make my separable ansatz. So the first thing I'm going to do is I'm going to say u is x times t. So here I'm assuming x is a function of x and t is a function of t. I'm just not going to write that repeatedly, just for speed, because we have, I'm fine going over a bit, but we have 15 minutes formally, right? I don't know if you guys have things after. Okay, so if I take these and plug them in here, what do I get? Well, if I plug it in here, for this bit, x does not depend on t, right? So it's a constant. I pull it out of the derivative, and I get t prime times x. Okay, on the other side, I get mu squared. When I take the derivative, t doesn't depend on x. So I get t x prime prime. Okay, so now what I do is I divide this whole thing by mu squared xt. So the reason why you want to divide by the mu squared is purely because if it's stuck over here on the x side of the equation, it makes things really ugly and really, like, you can still solve it, it's just awful. So you would basically, for you guys, that'd probably be a death spot, right? Because what you have to do to fix it is really weird, and you have to kind of mash space-time and do a transform. So if you have something like this, divide by whatever constant to make sure it's on the t equation. Okay, so after the smoke clears, here, this x cancels this x, this t cancels this t, this mu squared cancels this mu squared. So after everything's done, I'm left with t prime over mu squared t is equal to x double prime over x. Ah, this is the thing that I saw before. When I have this, I can assume a separable constant of the form minus lambda squared. Okay, so if you see this on the midterm or anytime you're doing this, your separation constant will always look like that. Why? Well, the solutions to this thing are sinusoidals, right? So because of that, you need things to match. Okay, so let me zoom way out and draw a little line there and zoom back in so I have more space. Okay, is everyone good up to here? I know I'm going kind of quick, but this is basically explaining, are all the steps explained to get up to this point? Okay, no questions, we're all good? Okay, so now I have two equations to consider. I have x double prime is going to be equal to minus lambda squared x, and I have t prime is going to be equal to minus lambda squared mu squared t. Okay, so now I have boundary conditions I need to solve. So to solve the boundary conditions, hey, there they are. Okay, so do the boundary conditions really tell me something about space or time? Well, physically, I actually have a rod here, right? This side is insulated. This side is held at 0 degrees, right? So since this guy is held at exactly 0, this term's insulated. And this is, like if time goes this way, if that's my time, these boundary conditions are held there forever, right? So the boundary conditions really tell me about time, or space, not time. So here, if I plug things in, I'll just do one analytically. So here I would get x prime, right? Because I took the x derivative of 0 times t of t has to be 0. Starting to lose my voice from, I'm talking louder than I usually do in class for whatever reason. But yeah, I feel the need to yell at you because you guys are so far away. Okay, anyway, sorry about that. So here I could just say, hey, if t is 0, then the whole thing is 0, so this has to go away, right? So that's my first boundary condition. The other boundary condition would just be x at pi has to be 0. Okay, so just chasing that out, those are my boundary conditions. So now I have initial conditions over here. I have, well, it's written in terms of u, so I'm not going to write it out explicitly. But I basically have some initial conditions sitting over here, okay? So now I have these two worlds, and I need to solve these equations, right? And to get the initial conditions, I actually need this data here. So now what I do is I solve a boundary value problem. Okay, so the solutions to this, x is going to be what? Well, since this is complex, I'm going to get sines and cosines. So here I'm just going to write them out as sines and cosines. You could use complex exponentials, but at the end of the day, your solution needs to be real. So it's your choice if you want to use complex Fourier and convert over, which that's one of the things we might not have time to cover in this session. But when I take this thing here and I chase it out, I'm going to get some constant that will, be a thing times my cos of, so I take the square root of that, so I would just get lambda times x plus another constant times sine of lambda x. Okay, so that's what I have for this. So solving that would give me this. Okay, so either know it or you could chase out the characteristic polynomial in the middle, but yeah, so you get something like that for this case. So now I need to apply the boundary conditions. Okay, so the first one is that the derivative at 0 is 0. So let's just compute the derivative. Okay, so here, derivative of sines, cosine, derivative of cosines, negative sine. So I'm going to get minus a lambda sine of lambda x plus b lambda cos of lambda x. Okay, so now I want x prime of 0 to be 0. Okay, so I'm picking 0 first just because it gives nice things. It doesn't matter what you pick. But if you do 0, you cancel the stuff in here, which makes things nice. Okay, so sine of 0 is 0, right? So this gives me that b lambda cos of lambda x has to be 0. Oops, sorry, 0. Cos of 0. Plug in 0 for x. Okay, so cos of 0 is 1. So here I get b is 0 or lambda is 0. Okay, so the lambda is equal to 0 case is kind of a degenerate case, because if lambda is equal to 0, then I just get, well, a constant solution, right? And if I have a constant solution, if I go all the way up here, in order to fit the boundary conditions, well, it has to be 0, because that one is 0, right? So this is degenerate because it's not particularly useful. It gives me one element of the Fourier expansion, right? Yes, you can use those properties of convolution freely. So I basically gave them in class as like, here's a thing. And for an example, I just made you prove it so that you would understand convolution, in theory at least, understand convolution a bit better. Okay, so since I have b is 0, my new x is just a cosine of lambda x. Okay, so now I want to use my other boundary. So if I do my other boundary, I have this at pi, so x at pi is 0. So in this case, x at pi is 0. Well, that tells me that 0 has to be a cosine of whatever lambda is times pi. Okay, so this gives me that a is 0. That's bad, because if a was 0, then I only have the trivial solution, or cosine of lambda pi is equal to 0. Okay, So here, I know what cosine looks like, right? So if I plot it, so cosine starts here, and then we do the blue, this guy, right? And I go blue the other way too. Okay, so here, this is at pi over 2, right? This term would be at my pi. That would be at my 3 pi over 2. This next one would be 5 pi over 2. So you can notice a pattern with these roots, right? So here, I need lambda. I need to pick lambda such that this is true. Lambda is the only thing I can control. So lambda is going to have to be equal to, let's just say, 2n minus 1 over 2. Okay, so if lambda is, say, 2n minus 1 over 2, where n is some integer, it's kind of nice because if n is equal to 0, I get the first one and so on. So I could split this up to start at 0. Okay, so now this is the key thing I wanted to get. So when I did this whole thing for solving the x equation, I want 2 bits of information. I need to know what is lambda, and then I need to also know what is x. Okay, so x is telling me the functions that I expand within, but those functions depend on lambda, so I need to know what the eigenvalues are. So if I have these eigenvalues, then I'm good. So if you just did n, so if I plugged in here, so if I did n, so if I plugged in n, I would have n pi over 2, right? So in this case, I would change in all the values. So I would have pi over 2, right? So I'd have this first one, but then I would also have 2 pi over 2. Well, cosine of pi isn't 0. So I can't do that one this way. I need to skip every other one because of the way that the roots work out. So it's purely because my roots here, where's my marker? There we go. Because my roots here skip, right? I have odd number over 2, odd number over 2, odd number over 2, and not arbitrary integer over 2. So yeah, so that's why I want to skip. Basically, here I don't want the pi or the 2 pi. Yep. So this purely comes around because I have these 2 boundary conditions, right? If I didn't have the, where's my mouse? No, go back. If I didn't have this derivative here, then I would have sine. I would be looking at the zeros of sine, and hey, sine is 0 at integer times pi, right? So there I would just use an integer times pi. But here I need it to be of this form because I'm dealing with cosine. Yeah, other questions? Yeah, so this is entirely a cosine thing, and you can feel free to use this type of an argument for figuring out what it is when, right? Like, I oftentimes just draw the picture. It's half the time it's easier to do that and to see the pattern than it is to have things memorized, even though I do have things memorized. Okay, so now what we've done is we have the x, we have this. So let's put this together to have a clean x. So x of x is going to be equal to what? Well, if I go up here, I know b is 0, so that term's gone. A is arbitrary constant, so I don't care what the constant is at this point in the problem, so I can drop it. So you can keep it if you want. It doesn't matter if you keep it or not, but you can drop it here because at the end of the day, you're going to use superposition to add in constants. Okay, so here I have my lambda is 2n minus 1 over 2 times x. Okay, and here I just say my lambda n is 2n minus 1 over 2. Okay, so this is what I wanted to get. And we're basically out of time, but I will finish this problem. It is recorded, so if you guys have something else to do, I'll finish it. So you can head off when the time comes for that. Otherwise, I'll at a minimum finish this. Okay, so that's my x thing. So now I'm done here. Like this stuff, this is dunesies. I'm done with it. So now I have to examine this thing. So before I can apply the initial conditions, I need a general solution, right? I need to solve the PDE. So far, I've solved part of the PDE, but I used the boundary conditions, like PDE with part of PDE plus boundary conditions. Now I need to solve the other part of the PDE. So here, I now know what lambda is. Lambda is lambda n, okay? So I can solve this. So here, if I chase this out, this would be E, right? You could divide by t, integrate. You get ln of t on one side is equal to the thing on the other side. You pull out the or take ln of both, or sorry, take e of both sides, pull out the constant, and you're done. If you wanted to chase out the details. But here, I would get e to the minus lambda n squared, mu squared, with a constant, but I don't care about the constant at this point because I'm going to introduce my own. Okay, so that's what my t is. Questions there? So this is just kind of basic ODE stuff. Yeah, you should be able to solve that pretty quickly. But that's what my solution will be here. Okay, so now if I take u here and copy it, so now I have my x solutions and my t solutions. So I can build up this mu sub n. So formally, you don't have to build up the mu sub n, but you can. So I can call the nth one would be some arbitrary coefficient. I don't know what it is. Cosine of 2n minus 1 over 2 x times, here I'll have my exponential term. And here I can clean this up a tad, which will make it a little bit uglier, but I'll just write it in manually. So here, that would just be 2n minus 1 over 2 quantity squared. Right? That's just plugging in my lambda sub n. So this is a single solution. So since I have a single solution to the differential equation that satisfies the boundary conditions, well, you can notice, hey, they're both, like over here, it's just 0 at the boundary. So if I add two of them together, it's still 0 at the boundary. Here, it's 0 at the boundary, the derivative. So if I add two together, the derivative is still 0 at the boundary. So because the boundary conditions are compatible with adding two solutions together and the PDE is compatible with superposition, I can add a bunch of these together. Okay, so I'm actually making a bit of an assumption here about convergence, but I can rewrite this as Cn cosine of my 2n minus 1 over 2 x. So Cn is an arbitrary constant, yes. And I just chose the name Cn. You could pick whatever you wanted for it. 2n minus 1 over 2 squared mu squared. And I can add, so I didn't have to add it here, but at the end, I do need it here, right? So you have your choice for where to add it. And if you really wanted to, like if you really wanted to be like very particular with it, you could add it here from where you chased this out. You can also add another constant here where you chased it out. You can multiply them together, absorb it to get an arbitrary constant, and then you could add it together. It's just mathematically, it doesn't matter because at the end of the day, I'm using linear superposition anyways. So because of that, I can just chase it out like this. So it's a spot where you can drop the constants. Mathematically, the constant is there, but just like when you were, say, doing the variation of parameters where you find a solution and then multiply it out and then chase out the details, you don't need the constant because you just need one solution. Yes, and do remember piecewise continuous, you need to be bounded for that. So yeah, so that is true. So if you're piecewise C1, then it does mean that f prime exists is the first one. Well, it exists outside of a set of finitely many points. And then f prime itself is piecewise continuous on its domain. So you can have some holes and gaps and stuff. Well, not really gaps. Okay, so now we have this. So what we have to do is we have to apply our initial condition. We're done with this, and we're done with this. We've solved these. Done. So now I need my initial conditions. So to do this, I need the appropriate series here. So I need to find an appropriate Fourier series for my thing. So for this case, if I plug in, oops, I dropped my time. That's bad. Time is important. So here, if I plug in t is equal to 0, I get u of x comma 0. In this case, that goes away. It's just going to be the sum from n is equal to 0 to infinity of Cn cosine of 2n minus 1 over 2 x. And here, do note that this is inside there. Okay, so what I need to do is I need to find the Fourier cosine series of this form. Okay, so it's a little bit wonky because I need to skip every other one of the terms, right? So if your function is sufficiently nice, you can chase it out. Otherwise, you could maybe do a quarter range expansion to pick up these terms. But nevertheless, in either way, you need to expand within this bases. You can do that since it's not our standard Fourier with all of the terms. It's a little wonky, but nevertheless, you can do that. So what you do is you take whatever your initial condition is, you expand it in terms of this bases, and basically to save myself some writing, you get, ooh, don't go down there. Okay, cut. Sorry about that. You get whatever your expansion is. And let's just pretend that I had a particular expansion. We'll say n is equal to 0. Let's just say my expansion was 1 over n. Okay, so what you do from here is you say, oh, by comparison, Cn is just 1 over n. And then what you give me at the end of the day is you rewrite this series where you plug in 1 over n for Cn. That's it. And then if we wanted to plot these and look at it, that's a thing we could do. Like I could build up a code real quick. I have some stuff floating around to compute Fourier series. I could tweak it if we wanted this. Okay, so this is the solution for that initial condition. Okay, so yeah, in general, you do have to compute the appropriate series there to chase out the details. You make sure they match, all that good stuff. I may or may not ask you to do that on the final, but either way, you're computing Fourier series, you're doing this, so it doesn't matter if I incorporated them or not. But yeah, just the main idea is you have to make sure you have the right bases. Right, so here, this is the right bases. Anything else would be wrong. And just because this was assignment 3, so I made a file for doing this in the case where I had a single cosine mode. So I'll just show you guys what that looks like. So are there other questions? I'm loading a thing. We can call it quits here. I didn't make it to complex form of Fourier series, but there's really not much there, so I'll TLDR that. So let's grab you and let me, yes, I can close the do, but I need you for research. St. Petersburg's gone. Okay, so if I just plot this guy, it's over here. Okay, so what happens, let me, okay, so I'm going to have to re-pull that over. So, yeah, of course. Okay, so there's my little plot. It starts and then it decays. So actually what I'm going to do is, if we want to actually get a view on this, let me cut out all this crap here. I don't want to make a video. Okay. And that should be sufficiently cleared. There we go. And the plot is over here. Okay, so this is what it looks like originally. And then as time goes by, it just decays. So notice here, this derivative at this point is always 0, and this point is always held at 0. So basically what's happening here is the heat is decaying and getting sucked out of this edge. So yeah, and I can do an example of C1, all that good stuff. So for instance, if I had both sides insulated, the heat would pull up to the, and it would average out physically. So yeah, you can do all kinds of little things like this. So expect something like this, maybe different boundary conditions, maybe different PDE, right? But the idea will be the same. You get your X equation, you solve it, you apply the boundary conditions, chase out what those are, get your bases, solve your time equation using your values of lambda n, put them together and do a Fourier series expansion to make them match. Okay, so if there are no questions, I will just delete all of that. Good? Okay. So, maybe, maybe not. So there'll be office hours. So there's office hours later today for sure. And I'll probably put office hours on Friday. But yeah, so as far as I had a couple questions about review sessions being ran by Stephanie. There, I actually need the hours to do proctoring and teaching. So sadly, I don't have those extra hours to put a session there. Okay, so C1, Piecewise C1, all that good stuff. Okay, so we'll just do this real quick. This will be the last thing I'll talk about here. So we start with the humble C. So continuous, yeah, you know what continuous is, right? So now that I have continuous, we can talk about piecewise continuous. Okay, so piecewise continuity is continuity's little cousin that's kind of a little bit more abstracted. So I can do things like this. I can have a discontinuity where I jump up here and I do some stuff. And I can do this finitely many times. So I can have finitely many of these jumps. And that's perfectly fine. I can't do something, on the other hand, like I go off to infinity and then I do something here. That breaks it. Like the singularity isn't a nice singularity, so it breaks it. If it's an essential singularity like that, I mean, technically, depending on your definition, that would be an essential singularity. But if it's a singularity that's not a jump discontinuity, then it's no longer piecewise continuous. I have another one for section 2 as well. So I have another one at, just for everyone watching, I do plan on going through similar materials there, 130. So I have another one at 130 to 1230. That one I'll probably start at close, like pretty much exactly 130, just because the other section, I teach 108 right beforehand, and they get out at 130. Okay, so here we now have our friend C1. This is a function that's differentiable, and its derivative is continuous. So I could do something like this, whatever, right? So if you wanted to plot, so if this is my f, your derivative, so it's not, the thing I'm going to draw is not going to be the derivative for that, but the derivative could be something with some kinks in it, something like this. This thing is is continuous, right? So this is my f prime. So if my f prime is continuous at this point, then I'm C1. Very good with that? Okay, so now if I want to talk about piecewise C1, well, just like with piecewise continuity, I remove the restriction that it actually is C1, right? So for instance, if you're continuous, you imply that you're piecewise continuous. If you're piecewise C1, you imply that you're piecewise, if you're C1, you imply that you're piecewise C1. So here, I can have a function that does some stuff, and I'm just going to draw this one. So I put some kinks in here, okay? This thing isn't differentiable at these points here. That kink, which is more of a flat thing, but it's not differentiable at, say, these points, okay? There's finitely many of these points where it's bad, okay? So outside of these points, so out of each one of these ranges, if I go down here and draw another thing, I can talk about, like, the derivative is a thing up to here. It's no longer a thing, so it's and then I jump, so now I'm decreasing, so I maybe jump down here, and around here it's not a thing, and now I'm increasing it again. So I go over here, and now I'm decreasing, so I'm over here, and now I'm increasing, okay? So that's what the derivative looks like, and at these circles, I can't talk about the derivative, okay? So the question here is this thing continuous, or piecewise continuous? So if this resulting function is piecewise continuous, then you're piecewise C1. So I have a function, I can differentiate it at all points everywhere outside of a finite number of points, and then the derivative outside of these finite number of points would then be piecewise continuous. Okay, so the way that it goes is continuity implies piecewise continuity, C1 implies piecewise C1, C1 actually implies continuity, right? Because if you're differentiable, then you have to be continuous. So this is kind of the little chart. There's no, actually between here, this would have to imply that as well. Yeah, so that's kind of the little way. This is kind of the hardest one to be in some sense. But yeah, actually, sorry, this is the hardest one to be, the one here. But yeah, so that's kind of the TLDR there. So if you want to check to see if something's C1, for instance, what you need to do is compute the derivative and check to see if the derivative is continuous. I'll do one thing here, actually. So if I go to the last assignment, was it 7? No, I don't think it was 7. Probably 6. So if I go to assignment 6, here there was a lot of common error things. The TA was overly nice to you guys. Was it this one? Yeah. So the TA was overly nice to you guys, and I just let them be. But here, if you want to actually test this to be C1, you need to actually compute the derivative, right? So if I want it to be legitimately C1, you have to do some stuff. It's clearly piecewise C1, right? So here, if I take my f prime as is, since this function is differentiable away from 0, I can just say, oh, I can do integration by part, or sorry, differentiation by parts. Yeah, so here I could take my x squared times 3 sine of 1 over x, and I could add to that my x cubed, so derivative sine cosine, 1 over x. Derivative 1 over x is x to the negative 2, so I get x to the 1 with a negative here. Okay, so it's a bit messy, but yeah, so I get that. So here, this is if x is not 0, right? And this bottom one is if x is equal to 0. Okay, so this top branch, that thing's continuous. Like, you can look at it, the limit as you, like, away from 0, there's no issues whatsoever, right? So this is immediately piecewise C1. The question is this actually C1? So to do that, I need to know what number goes here. And then I need to ask, does this number agree with the limit here? So you can say, hey, the limit as x goes to 0. But we have to show, yes, exactly. So that's exactly what you have to do by asking what goes here. So the first thing that well, not necessarily the first thing, but one thing that you need to know is the limit of f goes to 0, f prime of x, what is this? Well, this thing oscillates, that thing oscillates, but they're being multiplied by 0, so by the squeeze theorem, it's 0. Okay, just TLDR, did it real quick. I've chased that out in a little bit more detail, maybe. Did I? Yeah, I chased it out in more detail somewhere. Okay, so maybe. So now the next thing is you need to compute the derivative at 0. Well, the issue here is the function changes definition at 0, right? So it looks like this. At 0, I have the point here. I'll just do this in one note because I have higher resolution there. At 0, my function is 0. And away from 0, what's happening is it's going back and forth. It's decaying, but it oscillates really, really fast. So if you zoom in, like if this box is taken from here, what's happening is at 0, you have something that's going like, I'll do a smaller pin. You have, where are we? There we go. You have something that's oscillating. Oh, it's going to 0, so you have this like thing here. But it's oscillating back and forth between these infinitely many times between any finite point and going to here. So it's really bad. It's wiggling all over the place. So we have these two different branches. So what you have to do is use the definition of the derivative. So I'll just steal from here. Definition of the derivative at 0 is this, right? So if I'm away from 0, which you are if delta x is non-zero, I agree with the function. Okay, so you just evaluate this limit and you get 0. Since that's 0, 0 is what I get to put here, right? And then you just have to check like, hey, that limit of f prime of x is x goes to 0 is 0. This is 0. Hey, the derivative is continuous. Therefore, it's C1 in this case. Hopefully that makes sense with this. So if you want to show C1, you have to do that. If you want piecewise stuff, then like, hey, it's pretty clearly, I don't care what the derivative is at 0. It's still piecewise continuous, right? Like this could be 7. That could be 7 at 0. It's not in this case, but if it was, it would still be piecewise C1. Okay, questions here? If not, we can call it a quit for this section. Again, just for people watching live, not for people recording, there's another session at 11 or 1:30 to 2:30. Oh, I don't have office hours today. I apologize for that. Yes, there's another one at 1:30 to 2:30. And I'll probably put something at Friday avoiding noon because I was told that that was a bad point. So to be piecewise C1, the endpoints have to be. No. So to be piecewise C, the endpoints can do whatever they want. Oops, sorry about that. As long as they're bounded. So for instance, if I give you a function defined on this interval, this thing would be piecewise C1. Or if you wanted something even fancier, you could do this with a discontinuity. Okay, this would be piecewise C1. Yeah, so you can have jump discontinuities. So here, really, when you talk about piecewise C1, it's something like that, you need to talk about an interval. So here, if you're on the closed interval or the open interval, no matter what, this still is piecewise C1. If, like, there might be something you're conflating with this, we also have the periodic extension of f, right? That's the thing that gives, like, that's the thing that we converge to for our Fourier series. So if I take this, I can build its periodic extension by, say, hey, it's going to be open ball, the same structure here, open ball. Hey, that's already the average. So circle, circle. I know the picture's god awful. I apologize for that. Let me just make it better. For some reason, with this tablet, I tend to draw on a slant when I go over down here. It's not the tablet, it's a me thing. But yeah, so if I do this and draw it, make it a little bit more accurate, there we go. Circle, blah. So you'd have this thing, but if I want to do its periodic extension, you take the average between the edges, which just eyeballing it, it looks like the average is maybe over here, whatever the average is, and then you just repeat the thing. So here I repeat the same thing that was over there. So here I have open circle, I do the wee, go over here, close circle, I open circle, I wee over to here or whatever, and I close circle. So that would be 2 periods of the periodic extension. So something like that. But yeah, so don't conflate the two. If your original function is piecewise C1, then the periodic extension will be piecewise C1. Basically, if I'm piecewise C1 on this domain, then all I do by doing the periodic extension is I could introduce this point here where I could break continuity or being C1 itself. But the only thing I'm really adding is this and then recopying, where are we? Yeah, there. And recopying the function again and again and again, right? So you can't break piecewise C1 or piecewise continuity by doing the periodic extension. You can break continuity. So any of the theorems where it says like f sub p is piecewise continuous or f sub p is piecewise C1, those work for f as well. But if you need it to be continuous, like say if I want uniform convergence, so I need it to be continuous, in that case, you actually do need to check what the periodic extension is. So, as opposed to just looking at the function itself. I mean, you can look at the function and say the edges match, but yeah. Okay. Any other questions? Perfect. Yeah, and definitely converting from math speak to what it's really telling you is definitely a skill that has to be developed. And oftentimes, if I look at a lot of pure mathy things, I'll look at the thing like, okay, like it's a contraction map. It does this thing. Therefore, there's a fixed point. Okay, so contraction map's doing kind of this thing, and you build a mental picture of it. I'm picking on that one because that's the thing that I was working with semi-recently. So yeah. Okay, so that is it for this section. There is another session later today, and then basically there I'll probably start kind of covering the same material-ish. So if people have particular questions outside of this, feel free to ask. Like they're recorded, so yeah. Yeah, so that'll be a thing, and then I'll put something on Friday. I'll put an announcement probably on Wednesday, something like that. Okay, so I will talk to all of you later. I'm going to tell the recording thing to stop recording so it can